Okay, let's get started. This is week four, Introduction to Astrophysical Fluids. Let me share my screen over here. Right. So this is week four, Introduction to Astrophysical Fluids. Uh, my name is Rohan, and I'm a TA for this course. So yeah, let's start with a brief recap of the previous week, and then we will go through this week's content. Okay, so last week we uh, actually discussed the how we derive these three equations. So these are what we call the fluid equations, and the first one is the continuity equation, second one is the Euler's equation, third one is the conservation of energy, and fourth one is a equation of state, which is required because we have uh, six variables. And in order to have six equations, we also require an equation of state, which is basically a relation between the pressure, density, and the internal energy of the fluid. Right? So, yeah. So the unknowns in this equation are rho, three components of velocity, pressure, and internal energy. So there are six unknowns, and therefore we have six equations which can closely solve this system of equations for any system given the boundary conditions and the initial conditions. Now we also looked at some of the assumptions and under which this system of equation can reduce down to something even simpler. So for example, the first condition that we imposed was the condition of incompressibility, which states that del rho is zero. So the gradient of the density is zero. So the in the fluid there is no change in the density. And if we use the continuity equation, this condition in steady state reduces down to this condition del dot v equals to zero. So if we just expand this term, so this will be v dot del rho plus rho del dot v. So v dot del rho is zero and rho del dot v will also be zero. So del dot v is zero. Also, if you impose this condition on the second equation, you will get a condition like this, right? So you will get the pressure in terms of velocity, provided that you don't have any external forces and provided it's in steady state. So del t is zero. So, so there is actually one reduction of variables. Like you can have the pressure expressed in terms of velocities. So pressure is not no more an independently unknown quantity. So therefore, you can self-consistently solve these two equations because you will only have four variables and four equations out of these two, and therefore this energy equation will be decoupled in that case. Right. Now we saw another condition. The second condition that we saw is the barotropic condition, which states that the pressure is a function of the density. It could be any function of density. And in that case, the condition reduces down to del rho cross del P equals to zero, right? And then we studied about the Kelvin circulation theorem, which states that uh, that the so circulation is defined as capital gamma, which is uh, integration closed loop integral of v dot dl across any loop. So the circulation theorem states that if you you know consider this gamma, the circulation within a loop, it won't change as the fluid is moving. So no matter what is the circulation over here, the same circulation will be over here. And that condition reduces down to the fact that the vorticity, which is defined as the curl of V, is constant within this region, actually within this loop. Okay. So yeah, that is an important theorem, and maybe we'll see some of its uses later on. And then we tried to express all these three equations in their conservative form. So why this conservative form? Because this says something very physical uh, about the system. So for example, uh, the continuity equation is already in conservative form. So it states that um, the change in density with time is equal to the flux of density that is moving in or out through that volume, right? So this quantity is associated with the flux, whatever is inside the del dot gradient term. So that is associated with flux. So the change in any quantity with time is associated with the flux of that quantity. So similarly, the change in momentum with time will be associated with the flux of the momentum. So this quantity is recognized as the flux of the momentum. Similarly, the change in energy, it's again recognized as the flux of the energy, which is given like this. So yeah, and finally, we studied about the concepts of streamlines, streak lines, and path lines. So streamlines are basically lines which are tangent to the velocity direction. So these dotted lines here are the streamlines. Path line is the locus of all the points that the particle takes in the fluid, and the streak lines are the basically the locus of the path traced by the dye. If you insert a particle with a dye into the fluid, then the dye will basically follow this particle, and this will trace out this line which is shown in the blue over here. So these are the three concepts that we studied at the end. Okay, so this was a quick recap. Now we can move on to the this week's part if there are no questions. Okay, so okay, the first two slides are basically more on the uh, Boltzmann distribution and derivation of the you know fluid equations from the Boltzmann distribution, and then we'll go into some real life applications, right? So, for example, the stellar wind and the solar corona and those things. So those will be interesting. But here we just want to go through some of the derivations from the Boltzmann equation. So if you remember, this was the Boltzmann equation which we studied in week one, and this was the expression for the collision integral del F del T. And in week two, we derived the Maxwell distribution from this Boltzmann equation, and we said that uh, any distribution of particles in equilibrium will take the form of a Maxwell's distribution. Right? So yeah, so Maxwell distribution, this F will be given as m by 2 pi kt whole to the power 3 by 2 ex- exponential of minus mv square by 2 kt, right? So this we derived by taking the assumption that this is an equilibrium distribution, so this will go to zero, and then other steady state approximations, and we yeah. So this left hand side will become zero. So you are only left with the right hand side. So if you equate the right hand side to zero, then this part will become zero, and then from here we derive the Maxwell's distribution. So here we from here we found the value of f. Now we are saying that let's assume that the distribution is not in equilibrium. So, but the distribution is also not very far from equilibrium. So we consider that the distribution is a Maxwellian, so f naught plus some deviation from Maxwellian. So this is a small deviation. So this g is the deviation from the Maxwellian, and there is an assumption that this deviation should be small. So that is g must be much less than f naught. So f naught is the Maxwellian distribution. So we can safely assume that our f is of this form, f naught plus g. Now, if we do this, and then the collision integral will be uh, transformed like this. So instead of, so in place of f over here, so f prime over here, if we put f naught prime plus g prime, and instead of f1 prime over here, if we put f naught prime, f naught 1 prime plus g1 prime. And similarly for, we do the same for f and f1. So we will end up with this expression over here. Instead of this thing, we'll end up with this expression, right? And then we again assume that this collision integral will go to zero. And then finally, well, we don't assume that the collision integral will go to zero. That will only happen in case of the Maxwellian case. But here we are assuming that the system is not in equilibrium, so this won't go to zero. So here, what we will see is that this term inside this bracket reduces down to only uh, the last term. So all the terms reduces to only the last term, f naught 1 g. So that's what I have written. So f naught 1. So f naught 1 is the f naught at r, u1, and t, and times g, right? So this expression will reduce down to this expression. Now we take the assumption that, well, here we just do a simple integration. So we take f naught and g uh, out of the integral. Well, not f naught out of the integral, but we take g out of the integral, and we say that the g is weakly dependent on these uh, on the integral parameters like u1 and omega. So we take g out of the integration, and then we are left with this part only. So d3 u1 u minus u1 sigma omega d omega f naught. Now we already know that f naught integration of d3 u1 is basically the number density of particles, right? So again, we separate out this part again, u minus u1. So u minus u1 is u relative, and then sigma omega d omega. So this integral we separate out, and we assume that it's sigma total. U1 is basically the number density n, right? So this whole integral reduces down to this thing. This reduces down to f minus f naught by tau. So g is already f minus f naught, right? And where does this tau come from? So if you remember, so n sigma is basically inverse of the mean free path. So n sigma is 1 by lambda, which is the mean free path. So we have done this in week 1. So where we assumed that the particles are moving through a cylinder and there are collisions in the cylinder, and from the collisions and the collision cross section, we calculated the mean free path of the particles, and that is inversely proportional to n sigma. So n sigma is equals to 1 by lambda. So now 1 by lambda times u relative. So u by lambda. So u by lambda is the uh, mean time between collisions of two particles, right? So velocity by length is the time between two collisions. Right? So that's how we got this thing, F minus F naught by tau. Okay, now, so this is it. So basically, this Boltzmann equation will reduce down to the left hand side will be as is, the right hand side will be replaced by F minus F naught by tau. Okay, yeah. So this is what is called the BGK equation. Okay. So this is given as so if you just do G by tau and take tau to the other hand side, you will get this expression. So this is the BGK equation. Now in this BGK equation, just to see when like how does this new parameter G, how does the deviation of from the Maxwellian distribution, how does this deviation play a role? We try to see uh, this equation in a steady state, and we see how the gradients are behaving. So this deviation from the Maxwellian is caused by this gradient of f, right? So we take this term u dot del f and we equate it to g by f naught. So this will give you, so u dot del is basically, um, okay, let me see. Okay, so this del is the change in, well, well, I think this will be, there should be some tau factor over here. So tau u dot del is equals to, yeah, that's right. Mm, corrected. So tau u dot del, yeah. So if you look at this term, so this is tau u dot del equals to g by f naught. So if you take f naught to the other side, this will become this. Yeah. So now this expression is correct. Right. Okay. Now, okay, u tau. So u tau is basically, so u is the velocity, tau is the mean time between collisions. So u tau is basically lambda. So that's how we got this expression, right? So u by lambda is tau. So u tau is lambda. And del, so del is del x. That is just a gradient. So this is one. This is of the order of 1 by L length, right? So yeah. So lambda by L. So this side will reduce down to lambda by L. So I have changed this side over here. So this will correspond to lambda by L, and this will be G by F naught. So this order of magnitude calculations are very important in physics sometimes. So we, so what do we try to see from here is that we just try to assume what should be the order of magnitude of this G or lambda or L such that this G terms become significant. So in order for, so if you can see from this relation that if let's say lambda, the mean free path is very less than the length of the system, right? So let's say L. So in that case, this ratio will be very small. So in that case, G will be very small than F, much smaller than F. So in that case, this deviation from Maxwell distribution will not be significant, right? So there will be very little deviation. So we can see that in which case, uh, so if someone asks you like in which under which condition or which assumption we can neglect the deviation from Maxwell distribution, we can say that the mean free path has to be much less than the length of the system, right? Okay, right. So this was the order of magnitude calculation over here. Any questions so far? Okay. So now, okay. So now, if you remember, so we had derived these equations. So these equations were derived assuming that all the distributions were Maxwellian. Uh, but now we know that there could be a deviation from the Maxwell distribution, which is given by G over here. So now we want to understand how will these equations change if we have a deviation from this Maxwell's distribution. So if we have a non-zero G, right? So okay. So if you see over here, so okay, uh, so G is given like this, right? And if you solve G, you can get a term like this, right? So I will just show you how you get this term from this equation, from the PGK equation, how you get to this equation, right? Uh, so this was not derived in the lecture, but I will just give a quick derivation. Let's see. So okay, G is given like minus tau del del t plus u dot del plus e dot del u of f naught, right? So where your f naught is the Maxwell's distribution, which is given by m by 2 pi kt 3 by 2 e to the power of minus m v minus u whole square to get. Okay. Right. Now, okay, there is one number density also. So this is for one particle. If we have n particles, so this will be multiplied by n. So now f naught is a function of n, v, and t, right? So if we have to calculate del f by del t, so this will be del f naught by del n, then del n by del t plus del f naught by v, del v by del t plus del f naught by del t, del t by del t. Okay. And similarly, if we have to calculate del f naught by del vi, so this is the second term over here, this term. So this will be given by del f naught by del n by del vi plus del f naught by del vi. Sorry, this is del xi, not vi. Sorry. So del x naught. Right. Yeah. Xi, this will be xi, del vi, del xi, plus del f naught, del t, del xi. Okay. And as far as okay, so this is the A acceleration, right, not velocity. So as far as the third term is concerned, we will assume that this will go to zero because there are no external forces. So if there are no external forces, there is no acceleration. So we'll neglect this term fully. So, okay. Now, let me just write down del f naught by del n is given by f naught by n. Del f naught by del t will be given by m v minus u whole square divided by 2kt square minus 3 by 2t. So this will just come by taking derivative of this f naught. Right? And the last one is if we take del f naught by del vi, we will get F naught into MVI by KT. Right? So now simply you just put these values in this equation and then you will get del F naught del T, del F naught del X1, and then you can calculate G. Right? So, okay. So just quickly, I will just do it. So you will get del F naught del T as F naught times 1 by 1 uh, del N del T plus 1 by T del T del T M V minus C whole square by 2 kt minus 3 by 2 minus mv by kt dot dt, right? And del F naught del xi, if you do, you will get F naught by del n del xi plus 1 by t del t del xi and v minus c whole square by 2 kt minus 3 by 2 minus n by kt v dot del I v. Okay, and the last term is anyway 0. So from here, let me just quickly point out a few things. So here you have to apply the conservation equations. For example, using the particle number conservation. So if you remember the equation of continuity, so you will see that if you add these two terms, so the first term, so this term and this term, so first terms of both the terms will basically become 0 because this will satisfy the continuity equation. So which is del n del t plus v dot uh, v dot del of n, right? So there is a v dot v multiplied over here, right? So if you look at this equation, so this will be v dot del f naught del xi. So if you have to multiply this with v, right? So these two terms will cancel again by the assumption that the acceleration is 0. This will cancel, right? And we just assume that there is no change in temperature with time. So steady state. So this will also cancel. Now we are left with only these two terms, right? And there is, remember, there is a v dotted with this thing. So okay, so if you see this term, so this term is just a v dotted with this term will be equal to uh, the first term in the equation that we had over there. So let's see. Okay, so this is 1 by t del t del xi of ui times this thing, right? So similarly, you have 1 by t del t del xi ui. So ui will come from over here and times this thing. Okay. Now, how do we get the second term from this term, right? So this just involves a one-step process. So we can just write it down like so. Let's see. The second term is mu by kt dot v dot del of v. So this will be m by kt summation over of, let's say, ij. So which is ui uj del ui del xj, right? So let me just explain this thing. So v dot del is basically uj del xj, right? And then of u, that is ui, and there is also another u which is over there. So that is dotted over with this. Okay? So this is the expression, and from here now again we will use another property that we discussed briefly in the last week. So basically, as we said, that the multiplication of a symmetric and an antisymmetric tensor will be 0. So now if you see that this is a symmetric tensor, so basically ui times uj is equals to uj times ui. So that is, and that holds the property of symmetricity. Okay. But on the other hand, so this is not a uh, so on the other hand, this vector you can decompose into symmetric and antisymmetric components. So like by that I mean okay, let me write it down. So n by kt summation over of ij ui uj. So this can be decomposed as uh, half of del ui del xj plus del uj del xi. So this is the uh, plus half of uh, the antisymmetric part. Let me write down the antisymmetric values. So the antisymmetric part, when multiplied with the symmetric tensor, will cancel. This will be this. Whereas this part will remain. Now this is nothing but lambda ij. Right? So this is nothing but lambda ij. So from there we will get this equation, right? So lambda ij ui uj. Okay. Yeah. Now, okay, if you remember, so what are the consequences of this G being non-zero in this case? Right. Okay, so here we are getting 5 by 2, but in the derivation it is 3 by 2. Yeah. Yeah, you are right. So we will actually get 5 by 2. I forgot to mention this. So in this derivation, some, we did very simplistic calculation. So we ignored the uh, work due to the work done due to the pressure force. Right? So we only considered uh, thermal equilibrium condition, right? So it will be a bit lengthier, so that's why I didn't show it. But you can actually show that if you don't consider the, I mean, if you consider also the work done by the pressure force, you will also get another factor over here. Right? So this will just come from the fact that so if you include, so here if you see the del t, so this will have some work from the pressure also. So for example, let me show this equation. Right. So this energy is basically the temperature, right? So this is del t. So this won't be zero exactly, right? So here we neglected this thing. So there will be some work uh, done by this term, this pressure term, uh, which will contribute to the change in temperature. So here we ignored that term. So that's why we are getting factor less. Right? But you can try it out and then you will get this. This is the exact term. That way you will get the 5 by 2 factor. Okay. So now what are the consequences of getting uh, a non-zero G? So what? How will the equations change? So that was our main aim, right? So let's have a look at that. So firstly, if you remember when we are deriving the uh, when we are deriving the ideal fluid equations. So this equation. So the Q in the energy term got cancelled. So let me show you the. Yes. Okay. So these were the moment equations, right? Which were the uh, which we just obtained from the Boltzmann equation. Okay. Now then these had no assumptions in them. Uh, so these were the original equations, and then from there we assumed that the distribution is Maxwellian, and after assuming that we got these equations. Now, if we don't assume that the distribution is Maxwellian, then this q term will not be zero. So why was this q going to zero earlier? So this was because uh, this was an odd integral. So in order to evaluate q, so you have to multiply it with f naught, and f naught is an even function, and this is an odd function. So if when you evaluate over minus infinity to plus infinity, this q will go to zero. But now this is not the case. So f naught will still go to zero, but now our f is f naught plus g, right? So this g term will not go to zero anymore right now. So what will happen? What will happen to this Q? And similarly, so let me also just show you that similarly, what will happen is that earlier this pressure term was just P delta Ij, right? So here also, this pressure term was just P delta Ij. Now this pressure term will no longer be P delta Ij because this won't be diagonal anymore. So there will be like off diagonal components of this pressure tensor. So by off diagonal, I would like you to imagine any tensor as a matrix. Okay. So this pressure tensor will be a three-dimensional matrix, so 3 cross 3 matrix. So in a matrix, if earlier it was just P delta I, so that means the diagonal terms are just P, and the off-diagonal terms are zero. But if the distribution is not Maxwellian, so there will be some non-zero off-diagonal terms as well, right? Which we denote over here as pi ij, right over here. But we'll come to that. Let's see the q first. Let's see how the q changes if we consider this g. So again, like as I said, using f naught only, this q value would be zero. Now, from this equation, if you try to see what are the odd terms and what are the even terms, and you try to multiply this thing with g. So, for example, let's take the first term over here. So, the first term, there is one ui. So, there is one odd term, right? So, if it gets multiplied with this term, so this might become an even term, right? So then the integral might not be zero. Whereas in the second term, so there is only ui, uj, and u square, right? So if any one of ui or uj couples with, uh, let's say, uh, this thing, so this will become an even term, right? So there is, so then, sorry, let me see. Okay, so yeah, so in this term, what will happen is that if one of ui or uj couples with this term, then that term will become even, but there will be still be one odd u remaining over there, right? So there will be like 3 powers of u if you look closely, right? So that is basically odd. Well, 3 powers and then plus two from here. So basically 5 powers. So there will be an odd power of u. That's what I'm trying to say. So this term will go to zero. Whereas for q, we can consider this term only. So if you look closely, so if you do this integral, then q would reduce down to this expression, right? So this is the expression for. So if you write q as kappa del t, so then kappa will be this term, and del t is the del t del xi, right? And this, so how it comes? So just you have to multiply. So tau by tau t. So this factor comes over here, and then you just have 4 powers of u. So let me see other 4 powers of, yeah. So two powers of u from here, 1 power over here, and 1 power over here. So there are 4 powers of u, and then inside you have this thing as is, right? Right. Okay, so then integral over the whole d3u. So this will give you kappa, and this delta t, as I said, is given as del t del x. So if you perform this integral from minus infinity to infinity, you will get this thing. Right. So this thing has a physical significance that so Q is the heat flux, kappa is the thermal conductivity. So I think you're familiar with thermal conductivity in especially in metals. For example, if the collision time is very high, then the thermal conductivity will be high. If the number density is very high, then then the thermal conductivity will be high, and the temperature will be high, and so on, right? So you can get the thermal conductivity from these parameters. Similarly, for pressure, as I said, we can decompose it into a diagonal component, and then we can have some off diagonal terms. Now, what should be the off diagonal terms from here? Right? So, okay. So if you remember, the pressure definition was basically average of, okay, I have not written it anywhere, but let's see. So this will be average of ui minus uj times, um, yeah, ui minus bi times uj minus vj, right? So this will have two powers of u, basically, right? So if we have two powers of u, then let's have a look at the expression of g again. So for g, we will have, so this term, if you take the first term, so then there will be an odd power of u. So because there are already two powers of u in the definition of p, and there is one power of u from here, so there will be a third, three basically powers of u, right? And but from the second term, we'll get an even function because there are two powers of u from here, from p, and we'll get another two power from here. So this is an even function. So then pi ij will reduce down to uh, okay. So this ui uj, right? So definition of pressure is basically just average of ui uj. So then if we do average of ui uj times multiplied with this g function. So this, as I said, the first term will not survive, and the second term will be this thing, right? Now, okay. Now we can write pi ij is as pi ij equals to minus 2 mu lambda ij, where mu is this uh, whole integral except from the lambda factor. The rest of the integral is given as mu, right? Now, as I said, this pi ij is a 3 cross 3 matrix, but its diagonal terms should be 0, right? Because the diagonal terms are only considered in are already considered in the first part of the pressure tensor P delta ij. So if the diagonal terms has to be 0, that means the trace has to be 0. So uh, therefore, we know that lambda ij, the trace of lambda ij is not 0 because lambda ij is given like this. And if you take the trace, it will basically become divergence of V, not which is a non-zero quantity. So in order to have a zero trace for pi ij, so you need to define pi ij like this, right? So if you just take the trace uh, of this tensor, so okay, by trace I mean the summation of the diagonal components of the matrix. So it will be represented as summation of pi ii. So if you do the summation of pi ii in this term, so you can see that this reduces down to 0. So because lambda ii will be delta dot v, and you will have summation over 3 times. So yeah, so yeah, so this term and this term will basically cancel. Okay, okay. So okay, so maybe I'm going in a hurry, so let me know if you don't understand any step. I will write it down and explain it in that case. But yeah, this is the basic idea. Now, to determine the value of pi ij, we take one component of pi ij, let's say pi 1, 2, and in that case, we just put the value of I as 1, j as 2. So in that case, this expression will reduce down to this thing. Okay. And finally, from there, we can get the value of mu, right? So this turns out to be this thing, tau and k2. Okay. So this is the basic idea, but let me know if you. Uh, um, so I maybe rushed a bit, but uh, I can explain it in my notebook if you didn't get any step. Okay. So right. Okay. Now again from the from our old moment equations, right? So if we so this continuity equation will remain as is. Mhm. Mm. Okay. Yeah. Let me explain it. So so lambda ij is given as half of del vi del xj plus del vj del xi. Mm. Now, now let's say that the pressure tensor is given as P delta ij plus phi ij. Right. So, as I said, any tensor you can assume as a 3 cross 3 matrix. Right? So, P delta ij, what does it say? That this term, so, okay, so you know delta function, right? So, delta function is non zero if I equals to j, but is 0 if I not equals to j. So, that means that only for the diagonal components, only for the terms 1, 1, 2, 2, and 3, 3, this will be P. For the rest of the terms, this will be 0. So this is the first term, right? So this is the first term. Plus there is another term, which is pi ij, which will be 0 in the diagonal, but will be non-zero in the off diagonal term. So for example, this will be pi 2, 1, pi 3, 3, 1, pi 3, 2, pi 1, 2, pi, let's say 1, 3, pi 2, 3, like this. Okay. So this term can be represented like this, and this term can be represented like this. Okay. Now, we saw, so from this expression, as I said, we can just take mu to be all the terms except the lambda term, and then we can express pi ij as minus 2 mu. Well, all we express 2 mu as the rest of the integral, and then except the lambda part, and then we can express pi I as minus 2 mu lambda I. So pi ij equals to minus 2 mu lambda ij. Now we ask the question that, well, does this term represent a matrix like this? Right. Now, from the definition of lambda, we can see that let's take this term. So this term is 1 1 term of this matrix. So what will be the pi 1 1? So pi 1 1 will be minus 2 mu lambda 1 1. So which is equals to minus 2 mu. So from the definition of lambda over here, we can write into half into 1 1 will be del v1 del x1 plus del v2 del x2. Like this. So 2 2 cancels, so it will be minus mu del v1 del x1 plus del v2 del x2. Right? So now you can see that this pi 1 1 is not 0, but this should be 0, right? Because that's by definition. So in order to have uh, this pi matrix as a traceless matrix, we define pi as minus 2 mu lambda ij minus 1 by 3 del dot c delta is. Yeah. Now, yeah, this thing. So now, why this thing? Because now we will try to see whether the trace of this matrix, by trace, as I said, that it is the summation of these elements of in the diagonal. So we want to see if the trace of this matrix is equal to 0 or not. So this will be summation of pi I equals to 1 to 3. So this will be minus 2 mu lambda I minus 1 by 3. Delta II is 1. So, okay, so delta II, there is summation of outside, right? Summation of I. So del dot V delta II. Let me write it down like this. Now, let's calculate each term one by one. So let's calculate the first term, the summation over I lambda II. So lambda I is del v1 del x1 plus del v2 del x2. So this is for I equals to, uh, well, I think I made a mistake over here. So this is not v2 by x2. So this is lambda 1 1, right? Yes, yes. So this will be 1, all 1. Right, yeah. Hmm. Anyway, but the main point is that this was not 0 in this case. So this will be 1 1. And then similarly, del v2 del x2 plus del v2 del x2 plus del v3 del x3 plus del v3 del x3. Right. So this will become del v1 del x1 plus del v2 del x2 plus del v3 del x3, which is nothing but gradient of v. Okay. Now the first term gives you gradient of v. Let's see what the second term gives. So let me write it down over here. So second term is summation over of I. Yeah. Second term is summation over I, 1/3 delta II del dot V. So for I equals to 1, so this will be 1/3 del dot V. So del 1 1 is 1. So del dot V for I equals to 2 again del dot V. For I equals to 3 again, it's del dot V. So 3 times del dot V. So this will also give you del dot V. Right. Now you can see that, okay, the first term is also giving del dot V, second term is also giving del dot V. So therefore, this trace of this matrix will become 0. And that's what we want. So that's why we construct uh, the this pi ij matrix in such a way that this trace becomes 0. So this is just by construction. We don't uh, derive from this to this because you are just adding another term to it. And that's how we construct this pi ij tensor. I hope that is clear. Okay, right. Yeah, but yeah, this is a good exercise to do. And basically, this is a good trick that is used in many places. So basically, what you do in order to make a tensor traceless, so you just calculate the trace of this tensor and then just subtract the trace from this thing. That's what you do. So that's how you make this traceless, and then we obtain the value of mu, which is again tau n kt. And then, as I said, we can, you know, obtain our new equations from the moment equation. So for example, the continuity equation will remain as is. The first order moment equation. So here you see, earlier we had only P delta ij, so which will reduce down to del P, gradient of P. But now we have this extra term, which is this pi ij. So we'll have another term, which is del dot of this pi term. And this will give you this thing, an extra term over here. Right. So, so yeah, also you can see that if you do del xj of this pi ij, so if you see, if you do del xj of lambda ij, so you will get, so del xj of this term. So if you do del xj of this term, you will have del squared del xj square, which is the Laplacian, which is del square. And then you will have another term, which is del of del dot v over here, right? So which is also coming from this thing. So yeah, so maybe it will, you can try it out, and you'll, if you see, you will get this term at the end, okay, with this. But yeah, anyway, I think this will be simple to do. Now, for the third term, for the third equation, so here you see earlier we had q going to 0. Now we will have q not 0, right? As we saw from this. So q will be k gradient of tau, which will be which will give rise to this term. So del dot q will give rise to this term, del dot k delta tau, k gradient of tau. And this term, so p contracted with lambda, if you remember. So this term was giving rise to this term, but that was when we didn't have the pi term, right? So by including the pi term, you can write one extra term, but people generally don't write that term because that term is basically negligible in this equation, right? So people only consider only the first term of the pressure tensor for this term, for this equation, right? So these are the final equations that we have. So if you have to remember something from this course, I would say this is the most important set of equations that you have to remember, right? So the first equation is the continuity equation, second equation is the momentum conservation equation, also generally known as the Navier-Stokes equation, and this mu is known as the viscosity. Mu by rho is known as the uh, kinematic viscosity, and is also denoted as nu in some places. Anyway, so As I said, this is the Navier-Stokes equation. So, and this is the energy conservation equation. So these three equations in green box are the most important equations as far as this course is concerned, and in fluids in general. So everything that we every phenomena or every uh, um, astrophysical systems that we study can be studied using these three equations coupled with the equation of state, obviously, right? So that remains unchanged as is. So yeah, any questions or comments? Okay. So now we have derived these equations, and we will see the implications of these equations in astrophysics. Now this will be a bit interesting. So now, okay, hydrostatics. So from the name, if you see, uh, it describes some fluid which is in static equilibrium. And when we say, you know, static, we can already assume that there is no velocity of the fluid, right? V is zero. And if we, when we think about equilibrium or steady state, we can assume that the change of any quantity with time is basically zero. So if you just, so let's look at the this equation, the Navier-Stokes equation, and in that put the condition that v equals to zero and del t is zero. So this term vanishes, this term vanishes, this term vanishes. You are only left with del p by rho is equal to g. So g is the acceleration due to gravity, but it could be in general any external force, right? So let me zoom it out. So G, as I said, would represent any external force, right? So from the Navier-Stokes equation, under this assumption, del T 0 and V 0, you will arrive at del P by rho is equal to G. So what does it mean? It just means that the pressure force is balancing the gravity, right? And I should point out that this equation gets very important inside a star. So I mean, many people actually model stars or any objects which can be considered as fluid using this hydrostatic equation. So why stars? Because stars can be easily modeled as fluids. So for example, let's say our sun, this is a ball of fluid, right? Now, how does the sun holds itself, right? So because the gravity is pulling the matter inward, why doesn't it collapse? And form a black hole, or I don't know. So what is preventing the gravity? What is the force that is balancing the gravity? It's basically the pressure of the fluid, right? So for example, if you compress some fluid and you go on compressing it, you will experience an outward pressure on your hand, right? So you cannot compress anything to a infinitesimal small volume, right? So the fluid will exert a pressure on your hand, right? So similarly, the force that is balancing the gravity in a star is basically this pressure. And therefore, this is the equation for hydrostatic balance in any object. But people mostly use this for stars. Similarly, if you look at the other energy conservation equation, so if you apply the condition that del T is 0 and V is 0, so you will just arrive at this condition that del dot kappa del T is 0. Right? So these two are the equations for hydrostatic balance. Now, using these two equations, we can see that, like, we can explain many phenomena uh, in astrophysics by using just these two simple equations. So now, again, we will just use the same assumptions that we had done in the previous week as well. So, for example, let's consider that our fluid is incompressible. So if you remember that for incompressible fluids, the rho is constant. The del rho is basically zero. The gradient of rho is zero, so rho is constant. So from this equation, you get dp dz is equal to rho g, and this side is a constant term. So this integration becomes very simple. So dp equals to rho g dz. So rho g z, because this rho g is constant, and if you this p naught is just an integration constant, so this pressure will become p equals to p naught minus rho g, right? So this is something which we have studied in high school, right? But this is the origin of this equation. Now, another assumption is the isothermal case. So isothermal means that the temperature is constant. So in this case, the density was constant. Now the temperature is constant, right? So what we will do? So we know that for an ideal gas, P equals to rho kT, right? So this is the ideal gas equation. P equals to rho kT. So dP dz would be d dz of rho kT. So if you consider T as constant, so kT by m, and then we have d rho dz, right? So why we do d rho dz? Because here rho is not constant. Here temperature is constant. So we can take the temperature outside of the differentiation. But there should be some variation of rho with z. So this is just from the ideal gas equation. Now, from this equation, we can assume that this is equals to rho g, right? So dp dz is equal to rho g. Now, this is an integration. So this is a differential equation in rho. So you can like take the rho this side. So d rho by rho equals to g by gm by kt dz, right? So d rho by rho will become log of rho. So from there you can easily get this equation, and this rho naught is a integration constant, right? So these are two simple cases for which we can see that this hydrostatic balance equation is giving different profiles, right? So, okay. Now, an interesting case, which is generally, you know, followed in case of modeling stars, and this is the exact, I mean, this is what people do when they model stars. So they use this Lane Emden equation. So we'll see how we arrive at this equation. But I want to point out that this is the actual equation that people actually use to have models of stars. And yeah, and people do a lot of research work on this as well. So if you remember for the polytropic case, so polytropic means that P is a function of rho, and the function is defined as k rho to the power of gamma, where gamma is called the polytropic index, right? So the pressure is k rho to the power gamma. Pressure depends on your density in that way, right? Now, okay. So here we consider a spherical symmetry, right? So for example, a star is always spherical in nature, right? So we solve this equation. So instead of, solving this equation, we just take a gradient on both sides, and then we use spherical coordinates to expand this term, and this will become this thing, right? So this will become the Laplacian. And this del dot g from Newton's laws, we know that this is equals to 4 pi rho g. So this equation reduces down to this equation. And as I said, the polytropic equation is basically P equals to k rho to the power of gamma. So this is the polytropic equation of state, which is generally followed in all materials. I mean, mostly people model stars using this equation of state, right? And this gamma can be written as 1 plus 1 by m, right? So this is just a, you know, relation between gamma and n. So why we do this? Because it will become clear once we derive the Lane-Emden equation, right? So this is just a simple, conversion. So you can always write gamma as something, right? So now what we will do is we will try to. I guess we have understood like how we got this equation, but we have to see how we go from this equation to this equation, which is a more realistic equation that people use for solving hydrostatic balance in stars. Okay, so yeah, we'll go to the whiteboard again and we'll try to derive this equation from this equation, right? So, okay, so the hydrostatic balance equation was this thing. It was squared by rho into Qt equals to minus 4 pi rho g. And as I said, for polytropic equation of state, it was k rho 1 plus 1 by n. Now, another thing that uh, people do is that they model they assume that the density of the star at a given radius. So this star is a spherical object, right? So this is the center of the star. So the density at the center, let's say, is rho c, and the density varies with distance, right? So this is the surface of the star, right? So this, let's say, I denote the surface radius as this thing. But in general, the density will vary with distance, right? And the variation of density can be assumed in terms of this parameter theta, right? So we can always have a function like this, right? So any density variation is so all the variation in density of this rho is absorbed in the variation of theta with r. So theta is also a function of r, and so basically, so what this means for this density at the center to be uh, you know to be equals to rho c. So theta at r equals to 0. So center is at r equals to 0 should be equals to 1. So if this is 1, so that means that rho at r equals to 0 would be, this will become 1, so it will be rho c, right? You can see from here. So that's how we define theta. We just introduce another variable. Okay. Okay. And similarly, theta at the surface of the star should be 0. So because at the surface, the density will, there will be no matter, right? So therefore, the theta will become 0. So the density will become 0. So these are the two conditions by which we define theta. Okay. Now, using the polytropic equation of state, P equals to k rho to the power of gamma. So we can write it down simply like this. Right? So we can also write it down at Pc theta to the power of n plus 1, where Pc is given as k rho c 1 plus 1 to n. So Pc is nothing but, again, the pressure at the center. So just like the density at the center, we have the pressure at the center in terms of this thing. Okay. Now, from the equation, we get 1 by r squared ddr of minus r squared by rho c Pc to the power of divided by theta to the n d of theta to the n plus 1 dr equals to minus 4 pi g rho c theta to the power of n. Right? So this just I just put the values of rhos and p and yeah, those things. Yeah. Any questions? Yes. Right. Hmm. Yeah, so it will become clear once we uh, get to the Lane-Hamilton equation. Okay. It will become clear in a moment. But we can generally intake, it's just a change of variables from gamma to n. There's nothing special going on. Okay. I mean, we can just take it in another form, like we can do anything like 5 by n or 10 by n, right? But why this form? Why exactly this form? That will become clear at the end. So this just, reduces the equation, reduces the Lane-Hamilton equation to a very convenient form, right? So we'll see how this becomes convenient. So okay, now another thing. So this term d theta to the power of n plus 1 dr is basically 1 plus n theta to the power of n d theta dr, right? So if we just replace this term over here, so again we'll get from this equation n plus 1 pc 4 pi g rho c square. So we just, this rho c pc all are constant. So we are just taking the constant out of the different derivatives, and then this will reduce down to this thing, equals to minus theta to the power of n, right? Okay. So I guess at this step you can realize like why we took a form like this, because this reduces down to a very clean form theta to the power of n. So if we'd have taken something else, maybe 5 plus 1 by n, then this won't have reduced to this clean form, right? That's why we did this change of variables. So yeah, so now this is a constant term, as we can see, and this constant term we can just write that this is equal to a square. Right? So with a quick dimensional analysis, you can see that this has units of length squared. Okay. Okay. Now we do another change of variable, and let me first. Okay. So yeah, now we do another change of variables. So we introduce another parameter which we call psi, such that r equals to psi times a, where a is this thing. So people often do these kinds of variable change in physics. So such that this psi, so this a has units of, so a square has units of length square. So a will have units of length. This r also has units of length. So therefore this psi is dimensionless, right? So this, why we do this? Because this will be very convenient uh, for solving this equation. So I will explain it after I just write the equation in terms of psi. So if you just, write the equation finally in terms of psi, you will get 1 by psi square d d psi of psi square d theta d psi minus theta to the power of n. Okay. So yeah, so this is just coming from this equation. And this is a second order differential equation. So you need to have two boundary conditions. And those two boundary conditions are what we discussed earlier, that theta at 0 is 1 and theta as r star is 0. So this is a complete equation, right? Now, as I was saying that why we do this kind of a thing is because you see, so this is a, very simple form of differential equation which can be solved very easily, given given a system. And from here, you can obtain theta as a function of psi, right? And then, if you know theta as a function of psi, then you can model different stars, right? So, for example, why I'm saying different stars, you can choose rho c, the central density or the central pressure on your own. right? So you can choose any values of rho c and pc. Now, after choosing these values of rho c and pc, then you can know from this, by solving this equation, you can know the profile of theta, and then from there you can know the profile of this rho. And similarly, you can know the profile of p as a function of r, and you can know whatever the pressure, how the pressure varies throughout the star. Now you will also know how the density varies throughout the star, and so on. Right? So by just solving this equation and by choosing different values of rho c and pc, you can know the different values of this density and pressure along the star. Right? So also psi. Once you choose rho c and pc, so you can see from this equation, once you choose rho c and pc, you will get a fixed value of a also. Right? So rho c and pc will give you a value of a, and using that value of a, you can safely go from psi to r, right? So using that value of a, you can get theta as a function of r, and once you get theta as a function of r, you will get rho as a function of r, p as a function of r, and so on. So that's why if you hadn't done this, uh, going from this to this, then you wouldn't be, this wouldn't reduce down to this simple form, and then you couldn't choose any value of rho c and pc and then proceed forward, right? So then you have to solve for each stars individually. But here, you can just choose rho c and pc for any value that you like, and then proceed to get the profiles of this uh, density and pressure. Okay? So this is the Lane-Emden equation that we derived. I think in the lectures, professor has mentioned this equation, but he didn't derive it explicitly. So yeah, this would be a good exercise to derive this equation from here. Okay, now we will quickly go through the solar corona part. I think professor has explained this in his lecture. So yeah, again, as I said, I mean, for hydrostatic, we have seen that this simple equation can give rise to so many, beautiful things, uh, you know, like the Lane-Emden equation and the other hydrostatic balance equations, right? So another application is of the solar corona, right? So the solar corona is a gas which is emitted from the solar surface, and it's assumed, that the gas is uh, under hydrostatic balance. So for example, if you assume that the gas is under hydrostatic balance, so then this equation will reduce down to dp dr equals to this thing, right? And if you see, this is p by kt is rho, so this is coming from, sorry, p by kt is n times m is rho. So yeah, so this rho, if you transfer it to this side, so then you will get this equation. And similarly, this equation will reduce down to this equation. Now for solar corona, the kappa is assumed to be t to the 5 by 2, and by solving this equation, you can get this relation. And then putting this relation into this equation, so if you put the value of t over here, so and then solving this equation explicitly, you will get this expression. Right? So this was done in the lecture, so I not going into the detail. But if you have any questions, just ask me. But this expression has a problem, right? So the problem is that this, if you go to r tends to infinity. So for example, if you consider the origin to be the surface of the sun, right? Then if you go to, or yeah, at the surface of the sun where the pressure is P naught, and if you go to infinity, there is no corona, right? At very far distances, the corona will not be there. So at infinity, the pressure due to the corona should be zero, right? So, but if you, in this equation, if you put r tends to infinity, you will not getting zero. You are getting some finite value, right? So that is not possible, right? And that's where the problem is. And therefore, people, predicted that the solar corona is not under hydrostatics, equilibrium. So, in other words, this condition in solar corona will not hold. So, therefore, the velocity will not be zero. And people understood that, okay, in order for the solar corona to exist, the system must be expanding, the corona must be expanding. So, V should be some positive value, right? Now, okay, so those are basically, that's how we came to know about, I mean, theoretically, people have modeled stellar winds and those things from this surface of the sun, right? Okay, so, right. Now, so this is something that was not covered in the lecture, but the professor has covered about winds, right? And winds are very, I mean, theoretically, the solution for wind is very much, associated with the solution for accretion. So wind is just the reverse of accretion. So wind means, something, some matter going out from something, whereas accretion means the matter is coming in to the um, object, right? So, so since wind was covered in the lecture, so I thought maybe I will do the accretion part, and we can also see how the solution for the wind evolves from this accretion directly, right? So this is a very interesting, you know, a subject that people even is a very active area of research and something which I also very closely work with. And this is a very recent paper. Well, by recent, I mean in the 2010s, I think 2013 or 14. So this paper, uh, and people still work on these kinds of Bondi flows from, from black holes or these objects, right? So, yeah, but we would try to understand from the Euler equation that how we can model such um, astrophysical phenomena, right? So, okay. So now we will just do the same thing. We will take the continuity equation and we are again doing it all in steady state. So all the del t is zero. But in this case, the velocity is not zero because you see Bondi accretion. Okay, let me just tell first what the definition of what is Bondi accretion. So this was first discovered by a person named Bondi in I think 1960 or sometime around that. And it just states that you have a black hole or let's say any compact object, and if you have some gas or some fluid around that object, so it will fall into the object, and that fall will be radial in direction, so it will fall from in a radially symmetric fashion, right? Because of the gravitational pull of that object, so the gas will fall onto that object, right? So that is basically just the Bondi accretion, right? But it can be explained by these by whatever we have studied till now, by the Euler equation and the continuity equation. So this is the continuity equation, and since this is a spherical flow, we will try to do this in a spherical coordinate. So this continuity equation, as we saw in the spherical coordinates, will reduce down to this thing, and this is the Euler equation, which in spherical coordinates, the r component of this equation will reduce down to this thing, right? And obviously, we'll have the equation of state, right? Now, using these three equations, we'll derive the solutions for this Bondi flow. So let me go back to my notebook and start a new one. Okay, so this is the continuity equation as I wrote down. Rho 2 equals to 0. So this just means that r square rho v is a constant. Right? Now, this has a physical significance to it, right? So 4 pi r square rho v has a physical significance too. I just multiplied a 4 pi factor because if r square rho v is constant, then 4 pi r square rho v is also constant. So this is identified as m dot, which is also called the mass accretion rate. So what does it mean? So let's say you have a black hole over here. Right? Matter is falling into the black hole from all directions. Now, if you draw a spherical shell around this black hole like this, what is the mass per unit time entering through this shell? Right? So this area of this shell is given as 4 pi r square, and the flux of matter that is going through this shell is 4 pi r square times rho v. So this is called the mass accretion rate, and this accounts for what is the how much matter is crossing this shell per unit time, and this is constant in a Bondi accretion flow. So the flux at this radius, so yeah, I mean it will vary with radius of course, but this whole thing will be constant, right? Okay, so yeah, so this is what we get from the continuity equation. Now from the let's look at the Euler's equation. So v dv dr plus 1 by rho dp dr plus Gm by r square equals to 0. So this is the Euler's equation. And we also have the polytropic equation, which is given by k rho to the power of. Now, okay. So now let's see. So okay, one thing I forgot to mention. So when I write this v over here, so this v means radial velocity because this has only radial velocity. This doesn't have any, velocity in other directions. So Vr is not zero, but V theta and V phi would be zero. Right? Only radial fall. So here, that's why I only write the radial component of. So when I write V, so that means I am writing Vr only, and this is the radial uh, component of the Euler equation. Right? So this is the G term, and this is the del P by rho term, right? And this is the V dot del V term. And since it's steady state, del T is 0. Okay. So yeah, I think that's fine. Now, okay. Yes. So let's do one thing. So this dpdr term, so this term, let's express this in terms of rho. So dpdr is dp d rho and then d rho dr. So dp d rho by definition is cs square, the speed of sounds, times d rho dr. And why we do this, express this dpdr in terms of d rho dr? Because we can use the continuity equation to get an expression for d rho dr. So if we use this equation, right? So this equation will reduce down to, so basically, if you just do chain rule, so this will be 1 by rho d rho dr equals to minus 1 by vr square ddr of vr square. So this is just chain rule. So d rho dr times vr square and yeah, d rho dr times vr square and plus rho times ddr of vr square. Right? Okay. So now we can write this term dpdr as cs square d rho dr, and we can use the value of d rho dr from here. Right? And this will become, well, let's write 1 by rho dpdr. Let's see. Okay, let's write this term. 1 by rho dpdr will be cs square by rho d rho dr, and from d rho dr we can get minus cs square by vr square ddr of vr square. Okay, I think, yeah, that's correct. Okay, fine. Okay, now we just write this equation as this. So this will be v dv dr minus cs square by vr square uh, dv dr. Let's do one more step over here, maybe. So this will become, so if we just apply, let's a chain rule over here. So it will be cs square by vr square minus times b times 2r plus r square dv dr, right? Minus cs square. Mm, yeah, I'm wondering if I can simplify this. So, uh, okay, let me write down the final expression first, and then see if so this will reduce down to this thing. Okay. So, okay. So this gm by r square is this gm by r square. This is v dv dr, and for dp dr we have cs square d rho dr. 1 by rho dp dr is cs square by rho d rho dr. This is cs square. Okay, there is one row missing over here, right? Or not? No, I think that's fine. So this is coming from the continuity equation, 1 by vr square ddr of vr square. So cs square by So I just replace 1 by rho dr with this thing, c square by vr square, ddr of vr square, and I get cs square by vr square times, just expanding this, v times 2r plus r square dv dr. So this will be cs square, 2cs square by r plus or minus cs square by v dv dr. I hope I've been making mistakes. Yes. Well, okay, let me just continue and let me see it. So the final final equation, what they say is should reduce down to, yeah. Okay. So let me write down the final equation. Yeah. So 1 minus c square by v square ddr of v square minus gm by r square 1 minus 2 cs square r by gm. So this is what the final equation will come down to. Yeah, I have to check the steps in between. But yeah, c square. Okay, so yeah, you can check the steps in between, but let's see how this what this final equation means for now. Okay, so right now this is a first order equation in uh, velocity, right? So the only unknown you have over here is the velocity, right? Okay. Now we will define some terminologies over here. So okay. So first we'll see when the right hand side will become zero. So RH is equals to zero, and we will call that we'll call the radius where this right hand side vanishes as uh, critical radius. Let's say RC. Okay. So Gm by Rc square times 1 minus 2 Cs square Rc by Gm is equal to 0. So that means Rc is equal to Gm by 2 Cs square. Right. So this is the definition of uh, our critical radius. Now, okay. Now from this condition, from this configuration, we can see for Bondi flow, the matter is coming from very far and then falling into the black hole or the compact object, right? So we'll expect that the velocity at very far distance, let's say at r equals to infinity, the velocity should be zero, right? Because there is no gravitational pull. But as the velocity, I mean, as the matter is falling, getting closer and closer to the black hole, the velocity should increase, right? So that is the difference between accretion and wind. So for wind, the reverse is true, because for wind, what happens is that the matter is getting blown off, like from the solar corona, let's say. The matter is, blown off from the surface of the sun, and the velocity, uh, I mean, the velocity direction is basically just the opposite, right? So in that case, the velocity at the surface of the sun will be zero, but as it goes outside, the velocity will increase. So that is the reverse of accretion, right? So that's the only difference between accretion and wind. But we can arrive at both kind of solution from just this equation. Now, okay. Now, what has been seen? So this critical radius is some finite radius, right? So it is at some finite value. Let's say I plot the velocity versus cs, and this is the radial direction, and this is, let's say, your critical radius, right? So the matter will fall into the black hole. So let me just draw maybe simple diagram again. So matter is falling in, and let's say that this radius is my critical radius RC, and the matter is falling in from far into the black hole. So what is special at RC, right? So that's what we are going to see, right? So if you see that at RC, what is happening is that this term is becoming zero, right? So if the RHS becomes zero, so then there are only two possibilities. I mean, either this term is zero or this term is zero, right? So if RHS becomes zero, so the LHS also has to be zero. So either this is zero or del V square del R is zero. There are only two possibilities. Okay. Now we will look at one possibility at a time. So well, uh, let's look at the second condition first. So del V square is zero. So that means the so let's say this is the point where U by Cs is 1, and so del V, so derivative of velocity is 0. So that means the velocity will be flat at this point, right? Okay. So now, so this will be 0 at R equals to RC. Okay. Now, if R is greater than RC, what will happen? If R is greater than RC, so if you look at this condition, so if you go to very high radius, so what will be the value of this quantity? Will it be positive or negative? So this will be uh, a very low quantity, because you see this factor, R goes to infinity. This will make this term go to zero, right? So and also on the other hand, if you take R to be less than RC, so then what will be the sign of this quantity? So RC is Gm by 2c square, and so basically if R is less than RC, so this will also be a very weak quantity. So if you plot the graph, right, so this will come out to be like this. And this is under the condition, also another condition need to be satisfied, that V square should be less than CS square, right? But on the other hand, if V square is always greater than CS square, so you will get this curve, right? Okay. Now look at the second condition. So 1 by Cs square by V square equals to 0 at Rc. So that just means that V square equals to Cs square at Rc, at the critical radius. So that means in this graph, V by Cs should be 1. So this graph should pass through this point, right? Now here you can also assume that there could be two conditions, as I said, right? So okay. So as it turns out, these two solutions do not actually exist in nature. Okay. So but again, these are theoretical solutions, but these two solutions do not exist in nature. So let's not focus into that, but let's focus on the next two solutions that are coming from this condition. Okay. So let's see that we understand this very well. So as I said, the VC, yeah, question. Mhm. Yeah, so R cannot be 0 completely. So, for example, let's say that or a black hole, right? So the matter is falling in. So let's say a star is accreting. So the matter is falling in onto the surface of the star. So it will only go. The matter will only go till the surface only. Whereas R equals to 0 is the center of the star. So we are not tracking the matter to the center. We are just solving this equation only till the surface of the star, or in case of a black hole, only till the event horizon of the black hole. We are not going into R equals to 0. We are only going inside RC till the horizon or the surface of the star, right? Okay, right. So if you go, let me explain this graph. Okay. So let's say, let me explain in detail. So let's look at this equation. Okay. Now, let's consider this graph. So that means V square is less than CS square. So if V square is less than CS square, so then what is the sign of this quantity? Like, is it possible, will it be positive or negative? This will be negative, right? Because the denominator is higher. Sorry, denominator is lower. Huh. So this will be greater than 1, and 1 minus something greater than 1, this will be negative, right? So now let's write down dv square dr equals to this numerator divided by denominator. Now this denominator we know is negative. So I just transferred this term to this side. Right? Okay. So this denominator we know. So this denominator we know is negative. Now let's uh, let's see what about the numerator. So let's consider the region where R is less than RC. Okay. So if R is less than RC, then uh, this this term will be positive, right? This inside term, 1 minus this thing will be positive, but there is a negative sign inside. So this overall will be negative, right? So dv square dr is basically something negative by negative. So this will be positive, right? Okay. So now we can say, so you see that this thing is so beautiful is because we can say a lot of things about this equation without exactly solving this equation. Because you see, so dv square dr is positive. So that means in this region, the velocity will increase with radius, right? velocity will increase with radius, and then at r equals to rc, as we saw, this dv square dr will be 0. So this is a flat thing. And then if you see at r greater than rc, this term will be, this numerator will become, instead of negative, it will become positive, because this inside term will become negative. So this will become positive, and this overall dv square dr will become negative, because this thing is already negative. So this dv square dr will become negative, and then v will decrease with radius. Right? Is that clear? Okay. So similarly, if v square is greater than cs square, you will see just the opposite trend. Inside inside RC, this will decrease, and outside RC, it will increase. Just from the sign, just plus or minus of these terms, you can gather these things. Okay. So yeah, but anyway, these two solutions generally don't exist in nature, because, as I said, if you go very far out, your speed of sound should be something finite, right? But your velocity of the matter will be zero, right? But so basically, the physical case is, when for accretion, the physical case is, at the outside, velocity is less than cs, whereas in the inside, when as the matter is falling into the black hole, it will have very high velocity. It will have supersonic speeds. So v will be much much greater than cs. So it should cross this point, where v equals to cs somewhere, because outside v is less than cs, inside v is greater than cs. So the physical solution would be, uh, the physical thing would be to cross this point sometime. And that is what we'll get from this second condition. So as I said, the second condition states that v at RC is equal to cs at RC, right? Now, similarly, if you do the same analysis, that how the, you know, if you impose another condition that, okay, so for accretion, the condition that I said is v square tends to 0 as r tends to infinity. So v square tends to 0 and r tends to infinity. If you impose this condition, then your v should be very less at r tends to infinity. So it will start from here, and as it goes closer, it will be it will have very high speeds, right? Whereas for winds, v square tends to 0 as r tends to 0. So at very low radius, well, this is r tends to 0, r still not equal to 0. I should say, at very low radius, uh, the velocity will tend to 0, and then again it will cross this point, and then outward the velocity will increase. So this is the wind solution, and this is the accretion solution. So again, I think you can, from the signs of the, whether this thing is plus or minus, you can identify whether the velocity will be increasing or decreasing, and in which direction. You can do that analysis. Okay. Okay. So yeah, I think that is it. So these are the four solutions. Now these two solutions are also there, right? So these are just theoretical solutions, but uh, these are not possible, right? Because you see why these are not possible, because if you look at particular radius, so at this particular radius, you get two values of these velocities, right? So which is not basically possible. You cannot have two velocities of a single particle at the same point, right? So, but these two solutions, I'll just theoretically say where it comes from. It comes from the fact that the del V del R at the sonic point is infinity. So if you see, there is an infinite slope at this point. So if you consider, well, let me go back to the whiteboard. Just, I'll just explain this qualitatively. So if this is infinity, so that means that V equals to Cs. So if you just transfer this term to this right hand side, so this denominator will go to 0. So if this denominator instead goes to 0, so this dv square dr will be infinity at the sonic radius, right? So, but on the other hand, this term is not zero. So basically, the v square is equal to cs square, right? But yeah, but it never reaches the sonic point or the sonic radius. So anyway, these two are unphysical, conditions anyway. So let's not go into that. But yeah, it should be good to know that those two also exist theoretically. Let me. Okay. Okay, now coming to the last part. So, so you see, like, although people still work on Bondi flows and people write research papers and on this Bondi flow. So if you're interested, you can go through this paper. So this is a very recent paper and you know done by these two people who are pioneers in this field, and this is a very beautiful and elegant work, right? But the thing is, in general, in practical systems, like in practical um, observations, we do not generally see Bondi flows occurring. Well, the reason is that, in Bondi flows, what happens is that the matter is falling spherically onto the black hole or onto any compact object. But in nature, we always see objects generally have angular momentum, right? We do not see any object which is not rotating, right? Starting from our star to planets and everything. Everything is rotating, right? Now, if something is rotating and you know if the object, let's say a black hole, is trying to accrete the matter from that star or that rotating star or any object. So, in order to conserve the angular momentum, this matter cannot fall radially because it has some angular momentum present. So it should fall in that spiral path, right? Because it has some angular momentum and it will finally rotate and fall in the spiral path into the black hole, which will give you the structure of a disk. So, which mostly looks like this thing, right? Which is maybe you're familiar with what was shown in the movie Interstellar. Okay. So, those are actually what people generally see as disks. Now, when I say disk, so it will have some angular momentum, right? It won't be radial. So in our Bondi flow, if you remember, our assumption was that V theta and V phi were zero, right? But in this case, V phi will not be zero, right? In fact, V phi would be much, much greater than VR, right? Okay, we'll come into the assumptions, but let us first look at uh, some phenomenology. So, what is happening is that, as I said, the compact object is extracting the matter from the star, and the star is getting broken up, and it in the process it is losing some gravitational potential energy, right? So when you have two systems, the gravitational potential energy is given by gmm by r, the distance between the two objects. Now, as the star is broken up and is eaten by the black hole or the compact object, the gravitational energy of the system is lost. And this loss in gravitational energy is what is giving rise to this emission from the black holes, which we see, right? So, for example, this Event Horizon Telescope image, which has imaged this Sagittarius A star and M87, which are supermassive black holes. Sagittarius A star is at the center of our Milky Way galaxy. So, this emission, this light that is coming from these objects, is basically the conversion of this gravitational energy into this radiation energy that we see. Now, the loss of gravitational energy is given as gmm by A. So, m is the uh, mass of the central object. So, in this case, I have considered only a one solar mass. So solar mass is represented like this. So if at the center we have a object which whose mass is one solar mass, and the matter it gains from this star is, let's say, small m. So then it is converting. So this is just equal. So I just multiplied and divided by c square. So why I have done that is because this mc square is a measure of the rest mass energy of the matter, right? And this factor turns out to be very high. So from here we can estimate how much efficient are these processes. So how much percent of the rest mass energy is being extracted by this process of accretion. And it turns out that this is the most efficient process that exists in nature, even more efficient than a nuclear bomb or an atomic bomb. And these can release very high percentage of the rest mass energy of the matter that is being accreted. Right? Okay. So this gives you a fraction of the rest mass energy that is being extracted. Now, as I said, you have this, circular motion, and if you have a circular motion, you already know Kepler's laws. So Kepler's law states that the gravitational force is balanced by this centrifugal force. So if you just equate the gravitational force with the centrifugal force, gravitational force is gmm by r square, centrifugal force is m omega square r. So if you just equate those, you will get omega to be like this, or this form. So therefore, the omega in this accretion disk will vary as r to the power of minus 3 by 2. So as you go further and further, this angular velocity of the disk will decrease, okay, with this power law. Okay. Now, how is the angular momentum behave as we go further and further? So angular momentum is again given as mr square omega, and already got omega. So this angular momentum, on the other hand, will increase as r to the power of half. So the angular momentum of the matter outside is higher than the angular momentum of matter inside, right? Whereas angular velocity will be higher inside and lower outside. So there should be some mechanism of loss of angular momentum as the matter is falling into the black hole, right? So that is basically the viscous force that we also saw in the Navier-Stokes equation, right? So maybe in the next week we'll go through this prescription in detail, but we should remember the point that the angular momentum increases outward, and in order for the matter to come inside from like from outside to inside, in order for the matter to come inside and accrete, the angular momentum must be lost for the matter because the angular momentum inside is low. And viscous forces are the ones which causes the loss of the angular momentum. So this will come simply from the fact. So if you uh, remember this equation, okay, yeah, this Navier-Stokes equation. Let's see, yeah, this Navier-Stokes equation. So if you see this is the term for viscous force, right? Whereas if you write this, the phi component, the or the theta component of this equation. So, well, if you work in cylindrical coordinates, so it will be r theta z. So, if you write the theta component of this equation, so whatever factor that is causing the angular momentum, so from this term you will get the angular momentum. So, v phi or v theta is basically the angular momentum, right? So the change in angular momentum is caused by this viscous force. So this directly comes from this equation. So we'll see later in detail by solving that equation explicitly in the next week. But yeah, I was just pointing out phenomenologically how this happens. And okay, so again, for the Bondi flow, as we said, the assumptions were VR is non-zero, rest as zero. So what are the assumptions in this case? So in this case, as I said, we'll be working in cylindrical coordinates, and the del theta, which is the cylindrical theta coordinate, will be zero. So we will assume that the matter is symmetric about theta, right? So there is no change in velocity, or so given a particular theta, the velocity or the all the things should be same, right? So yeah, basically in a circular motion, So it should be uniform in that particular circle or in that particular ring. Okay. So that's what it says, which is not a bad assumption. Another assumption is, as I said, the v theta will be much, much greater than Vr because, as I said, this is a disk and the matter is rotating in a Keplerian motion. So matter is rotating, is having a circular kind of motion. So v theta, whereas radial motion is very less. The radial velocity is very less, unlike in the Bondi flow case. Okay. So here v theta is dominating, right? And Vz, as I said, Vz will be zero because there is no force in the z direction. So these are just our assumptions. While we'll also assume that the del Lz is ideally not zero. So the variation of velocity might not be zero in the z direction, but we'll just assume that the radial velocity and the theta velocity will not vary along the z direction. So therefore, you can assume that this is kind of a, you know, what can I say, a torus kind of a shape, right? And the matter is rotating in a Keplerian flow um, in that torus, sort of like that. Okay, so that are all the assumptions, and yeah, we'll solve these equations with these assumptions in the next week, and we'll see how the solution comes out and how is it different from the Bondi flow. And so this solution was first given by Shakura and Sunia, and so these kind of disks are therefore called thin disks, or also called Shakura Sunia disks, and named after who came up with the solutions. Also, they are also called Novikov-Thorne disks. So basically, Sakura Suniev gave a Newtonian prescription of these kind of disks, whereas Novikov-Thorne solved these equations only, but in a GR, general relativistic framework. Okay, so those are the same things, but yeah, I think that is the GR version of thin disk, and these are the Newtonian version of thin disks. And yeah, I guess that is it. And yeah, but one thing to note is that these thin disks are not the only kind of disks that we observe in nature, right? So along with that, we also observe some disks which are uh, so why the assumption thin disks, right? So here these disks are geometrically very thin, right? Sort of whatever is shown in the picture over here. But generally, we also see in nature disks which are geometrically thick, right? So as I was saying, it could be a torus, and the and this assumption that v theta is much much greater than Vr might not hold. It might not be a Bondi flow kind of case, but it should be completely general, right? So it could be, the radial velocity could also be significant, and instead of just the angular velocity dominating. So yeah, those are just for research purposes. So those are basically called advection dominated accretion flows, right? ADAF. So it was worth pointing out, but yeah, and those are also active area of research in this accretion risk. Okay, so for reference, as I was saying that I already mentioned this book for the Boltzmann equation and those derivations. And for fluid mechanics basics, you can go through this book, chapter 1 to 4. For the accretion part, whatever we have discussed in the Bondi flow and accretion disks, I think this book is a very standard book, Accretion Power in Astrophysics by Frank Fungarainen. You can go through chapter 1 and 2 for the uh, for the Bondi flow. And you can also yeah, chapter 1 is more general accretion, and 2 is more focused on Bondi flows. And I think in future chapters, you can also find thin disks and those things. So this is a book which is focused only on accretion. So you can go through that as well. Okay, questions. Okay, not then probably. Yeah, at least I think what I did in the notebook, maybe, you know, try to have a look at this again and derive this. Uh, yeah, I skipped a few steps over here, but if you do it carefully, we'll get to this. And yeah, I will post these notes, and I'll try to complete the steps in between before posting. But you should also do it on your own, how to go from here to here. But I think the main uh, message is clear how to draw this graphs without explicitly solving this equation. Right. So yeah, that is it. Okay, if there are no questions, we can end the call and see you next week. Yeah, thank you. Yeah. Okay, bye. Good night.